Today we are going to discuss the pattern searching algorithm using the suffix trie. Okay, so let me write it down. Pattern searching algorithm using suffix trie. Okay, so first let's understand what the problem is. So suppose you are given a text and you are given a pattern and you are asked to print or find all the occurrences of pattern in text. Okay, so in my previous video, okay, I have discussed total three approaches. One was the brute force approach. So what we do in the brute force approach is we take a pattern and we slide over the text at each index and we do the comparison. So the time complexity of that approach was mn, which was not linear. The second approach that I discussed was KMP, in which I computed the LPS table. There was a separate video on this, and the time complexity was m plus n because we compute the LPS table for the pattern, which takes O of m time, and then we use that computed LPS table to search the pattern in the text, which takes O of n time. The third approach was Rabin carp approach, and the time complexity was this one was m plus n, because here we compute the hash for the pattern which takes O of m time, and then we do the rolling hash and we keep computing the hash for the text. We do the comparison only if the hash for the pattern and the text matches, otherwise we don't compare the characters. So that was a Rabin carp. So in both of this about to approach KMP and Rabin carp, what we are pre-processing the pattern, and there is a time complexity associated with that. But with the current approach, with the suffix trie, what we are going to do is we are going to pre-process the text, not the pattern. Okay, and there is a cost, of course, associated with that pre-processing. But then, after doing that pre-processing of the text, the time complexity to search the pattern is only O of m. So this approach is very good when the text doesn't change often. Okay, the text is not changing frequently and there are many search queries. In that case, this approach is very good. Now, before we go into the detail of the algorithm, right, you need to know how to build the trie. So I'm going to show you how to build a standard trie. Okay, so let's look at the example of how to build standard trie. Okay, so suppose you are given a list of words like bear, then you are given bell, you are given bed, you are given bull, then you are given buy, then you are given sell, then you are given stock and stop. Okay, so these are the list of words that you are given and you need to build a standard trie. So the standard trie always has a root node, and then we check to see, now the first word is bear, so we check to see whether the root node has a beak. It doesn't, so we create a node B. Then this one doesn't have A, so create a node E, then A, and then R. Okay. Then Bell, so BELL. Then Bid, so BID. Bull, BULL. Then Buy, BUY. Then Sell, SELL. Then Stock, so STOCK. And then we have Stop. So that is a standard try. Now this has too many nodes. So the nodes are whatever the, suppose each word, if there are n words and there are k letters in each word, then it's n into k nodes. So we can also build a compressed try by joining all the single nodes. So we can join, like for example, BEAR. So these are a single node. So what we're gonna do is we're gonna join it here, AR, and we're gonna remove this node. Then LL is a single node. We can join it and we can remove this. ID, that is also a single node, so we can join it and we can remove it. So we're gonna store here ID in this node, not just that character I. So here also LL, so we're gonna join it and remove this. And here also ELL, and we're gonna remove all this. Then we have STOCK. CK, we're gonna join, remove this, and TO also we're gonna join and remove this, and this is directly connect to CK, and TO directly connects to P. So that's how we build a compressed try. Let me draw it again, okay? So compressed try. So we have a root node, then we have B, then we have E, and then we have AR, and then we have LL, Bell, and then we have ID, Bid, then we have ULL, Bull, Y, Buy, then we have S, and then we have TO, CK, and P. So that's the compressed try. Now let's go into the detail of a steps to build the suffix try, okay, from a given text, okay. So to build a suffix try, what we need to do is we need to generate the suffixes, okay, of the given text. And then we need to consider all the suffixes as individual words, and then we need to build the try or the compressed try out of it, okay. So for example, let's see, you are given a text something like banana, okay. So that's the text you are given. So what are the suffixes of banana? So that is a, dollar, we are adding dollar at the end, na, dollar, ana, dollar N A N A dollar A N A N A dollar and BANANA dollar. So these are the suffixes of the text banana. So if you look at the suffix, right, it always starts at any of this 0, 1, 2, 3, 4, 5, and 6, any of this index, and it always end at the end. Okay, so it always end at the last index. So everything ends in A, the last index, which is this one, right? And this starts at index, let's say this starts at index 501, 2, 3, 4, 5. Okay, so this starts at index 5, 4, 3, 2, 1, and 0, right? So let's build a try out of it. Let's build a standard try out of it. Just a second, let me scroll this. So let's build a standard try out of this, okay? So you have a root node, then you have A, and then there is a end node, dollar. Then we have A, and then NA, right? So we have N, A, and then we have dollar. The next one was ANA, A, N, A, dollar. Then it was NA dollar, NAN, N, A, dollar, N, A, dollar. Then the next one was ANA dollar, and then it was banana. So B, A, N, A, N, A, and then dollar. So that is a the suffix try. I mean, you generate all the suffix of a text and then you build the try out of it. Okay, so that is a suffix try. Now, if you build a compressed try for the suffix try, how it looks like? How does the compressed try looks like? So the compressed try looks something like this. Let's see. For this banana, we are going to make a compressed try. Okay. So the compressed try. So we have a root node. We have a root node. Then we have a dollar. Then we have an a and a dollar. Then we have ANA, A, N, A, and then we have dollar, and then we have NA dollar. So N, A, dollar, and then we have again NA, NA, dollar, and then we have banana dollar, B, A, N, A, and A, and then dollar. You can also append this dollar here, remove this, and I mean, this will stay here. This is gonna stay here, but you can remove this and append it here. You can do that. Okay. So if you look at the substring of a text banana, okay. So what are the substring of a text banana? Let's see. We have banana, okay. So what are the substring of a text banana? It could be B, it could be BA, it could be BAN, it could be BANA, and so on. And it could be A, it could be AN, it could be ANA, it could be ANA, and so on. And it could be NA, and so on. And it could be A and so on. And so these are all the substrings of the text. So if you look all the substrings of the text, right, they are the prefix of our suffix list. So if you look at our suffixes, right, all the substrings, they are the prefix. Okay, so let's take a substring BAN, right? It is a prefix of this substring BAN. Let's take some other one. For example, let's take a substring ANA. Okay, so ANA is a prefix of this one, right? Let's take another substring NA, right? So NA is a prefix of this one here, right? So can we say that all all substrings of a text is prefix of all the suffixes? So so basically what is a substring? It starts at any index and it ends at any index, right? And the suffix, right, the list of suffix that we have, right, it started at index 0, 1, 2, 3, 4. So if there is any prefix, sorry, any substring that is starting at index 2, then it would be a prefix of this suffix, right? So all of the substrings, they are a prefix of this 0 to 5, the suffixes. If you look, you can generate all the substring and you can check against the suffixes. They will be the prefix of this suffixes. This is very much true. Okay. So now what are the application of the suffix trie? Okay. There are many applications of the suffix trie. Okay. Number one is the pattern searching. Number two is finding the longest repeated substring. Okay. Finding longest repeated substring. Number three is finding longest common substring. Longest common substring. Number four is lowest common, finding longest palindrome in a string. Finding longest palindrome in a string. And number five is lowest common ancestor. Okay. Now, what is the time complexity to build the suffix trie? So, if we look, we have how many suffixes? We have the length of the string is n. So, we have n suffixes, and the length of the maximum length of the suffix is n, right? And then we are adding a node for the each suffix, right? If we use a standard trie, right? So we have n suffixes, max length of the suffixes n. So the time complexity to build a suffix trie is n into n, which is n square. But there is also another, I mean, you can build a suffix trie using Yuko, Yukonan's, yeah, Yukonan's algorithm. and this is gonna take a linear time to build the suffix trie. Okay, so to build it using a unicorn is O of n instead of O of n squared. Okay, I mean, it's very hard to implement the Yukonan's algorithm. Just mentioning it is good enough. I mean, um, implementation is very hard for the Yukonans. So now, now let's go over the implementation. Okay, so how we are going to implement this algorithm is we are going to, for example, let's take one example. Okay, we are given text which is BANANA. Okay, and the pattern we are given is NA. Okay, and the output that we are expecting is that the NA occurs in this pattern at index 2 and 4. So that's what we need. Okay, so what we are going to do is we are going to construct first step. Okay, the first step in our approach is to construct the suffix trie of all suffixes. Okay, why? Because because all substrings, they are prefix of suffix. Okay, and the construction time has O of n square, which you know it, but the pattern searches only O of n, right? So so what we are going to do here is, let's say we have generated all the suffixes and then we have built a trie out of it, which is this one, which is this one. Okay, now here, right, we are also going, where there is a dollar, we are also going to store the index. This is a, this suffix that started at index 5, this suffix that started at index 3, this ANN that started at index 1, this started at index 4, this started at index 2, and this started at index 0. So now, if we want to search the pattern NA, we need to find where does this pattern occurs in a text, right? So what you'll go, you'll traverse the suffix trie and you'll see you have N and then you have A. Once you found the pattern here, right, you need to collect all the dollars that A has. So A has $2 and then you need to grab this index and you get the answer 4 and 2. NA, you found a pattern here, and then for all the children you collect the dollars and check the start index, I mean get the start index and save it. So this 2 and 4, so the pattern NA occurs at index 4 and at index 2. Very simple approach to implement. Okay, so we are going to create a try node for this one, and let me give you how the try node looks like here. Okay, or we will do it later on how the try node looks like, but let's do this. Okay, let's go to the implementation. That's it. That was the suffix try. Now let's go to the implementation of the suffix try. So I'll just go to the implementation. Okay, now let's write our approach once again so that we know what we need to implement. So first thing is all substrings, they are prefix of suffixes, right? So once we have a suffix trie, it's easy to find any substring because ultimately all the substrings, they are the prefixes of those suffixes, right? So you just traverse the tree and you'll find a substring. If you find it, you found a match. And to get the index or anything, just collect the dollars that has a starting index stored in them and you'll get the index. So if you create if you create a suffix trie with all the suffixes, then search the pattern in suffix trie. It's very easy. So if you create suffix trie with all the suffixes and then search pattern in suffix trie. Very easy. And also maintain indexes in trie node so that we can return those indexes. We can return the index where the pattern is found in the text so that we can return index where the pattern is found. So you need to maintain also maintain the start index, right, wherever there's a dollar. So let's do the time complexity analysis. The time complexity, so the construction time of the suffix trie using a standard trie is O of n square and search pattern is O of m. Okay, what is the space complexity? So for if you are using a standard trie, then for each suffix and for the maximum length of the suffix is n, and we have n such suffixes. So the space complexity is O of nk, where there are n suffixes and where k is the maximum length. Okay, so it's nk where there are n suffixes of length k, because for each character we're gonna have a node. Okay, so now let's implement it. Okay, so let's do this. Let's make a trie node and see how does a trie node looks like. Okay, so we are going to create a trie node. So public class trie node. The trie node has all the children's in it, right? So we are going to do a hash map of character and the trie node, right? Because it has a character and then that child also has a lot of child. I mean, it's like you can also implement it using, like, if you have a 26 characters, all are caps, then you can just take a root and a 26. You can use the array also. But map is easier. I mean, if the character stat is very varying, you don't know what the character stat is, you can use the hash map. Children. Then we also need to mark the node which is end of a word, so that we know that here the one word ends. So public boolean end of word, and then in that dollar node, right, we are storing the start index. So we need that start index, and then public trie node, and then we have children is equal to new hash map end of word will be false. You can set it to true when the word ends, and then start index will be equal to -1. unless you set it. So that's the constructor, and that's our try node. Okay. Now let's implement it. Okay. So let's implement our class where we are going to search a pattern inside a text. Okay. So we have a public class pattern searching. Okay. And then we have our try node, private try node, root node, right? And then we have a method that is public list. We are going to return the indexes. So list of integer where the pattern occur, right? List of indexes where the pattern occur. So list, and then the input is text and pattern. Okay. Now we are going to build first of all suffix try out of this text, and after that we are going to search pattern in that suffix try. Okay. So first let's build a suffix try. So public void build suffix try, and then we are given a string text. Okay, let's build a suffix try. Let's initialize the root as an empty node. Right, for building the suffix try, first you need to find all suffixes. Right, what are the all suffixes? The suffix starts at index 0 1 2 3 4 up to n, and then it always ends at the end character. Okay, so for integer I is equal to 0, I less than txt dot length I plus plus. Okay, and we got our suffix, so we're gonna insert it into our try, the text dot substring that starts at I and ends at the end. And we also need to give them the index for storing it, right? The starting index that we are storing it at a dollar node, so we also need to pass that. Okay, and there, now let's write how to void insert, and then we have a string word that we are going to insert in our try, and then we have an integer index. So our try node current is equal to root. We're gonna take a first character for integer I is equal to 0, I less than word dot length I plus plus. So our first character ch is equal to word dot character at I. So that's our first character. And then try node is equal to, we're gonna check if our current node has children with that character. Okay, so children dot get character ch, right? If the root node doesn't have that character, then we're gonna add it. So if node is equal to null, then we're gonna create a new try node, and then we're gonna add it to the children, current dot children dot put the character and the node. So that's it, and then current is equal to node, and then we're gonna search for the next character. That's how we're gonna enter all the character. And at last, right, when we are done, right, entering the whole whole word, right? We're gonna add the dollar node. So try node, dollar node is equal to new try node. And then current is pointing to the last character of the word. So dollar node dot start id x is equal to index that we passed on initially, and current dot children dot put, and then we're gonna add a dollar, and then we're gonna add a dollar node, and there you go, our try node is our try suffix try is created. Now let's write a search method. Okay, how to search a pattern. So that is public, it returns the list of indexes, a list of integer, search pattern. Okay, and then we have this pattern that we need to search. Okay, so let's create a result, integer, list of integer, result is equal to new array list, and then let's search it. So let's traverse the suffix trie tree and search it. So try node current is equal to root for integer I is equal to 0, I less than pattern dot length I plus plus. So the first character of a pattern, which is ch, is equal to pattern dot character at I, and then try node is equal to current dot children dot get ch. If we found it, great. If we don't, if node is equal to null, we are not able to find that pattern, so just return the empty result. But then if we found it, search for the next character. So current is equal to node and keep searching for the next character. This closes the for loop, and then you collect, once you found the pattern at the end of the for loop, collect all the indexes from the dollar node using what? DFS. So collect dollar from we found the pattern, so this is the last character of the pattern node where it's pointing, and we're gonna pass the result, and we're gonna collect all the indexes, and we're gonna return result. So let's collect dollars using the DFS. Okay, very easy to implement the DFS. So public void collect dollar, we have a try node current, and then we have a list of integer result, right? So we're gonna do a DFS. So for map dot entry, we have a character, and then we have a try node, and then that's a child. So current dot children dot entry set. Okay, so we took a first child, and we see if that child is dollar, if child dot get key is equal to dollar. If that child is dollar, what you are going to do? You're gonna do result dot add child dot get value, which is a try node dot start idx, right? But if that child is not a dollar, right, then you're gonna do a recursive DFS call, and then child dot get value, which is a try node, and then the result. And here we are done. So that closes the for loop and that closes the function, and we are done with our implementation of a suffix trie for the pattern searching a pattern in a suffix trie. Thank you for watching a video. In the next videos, I'm going to cover the application of the suffix trie. Thanks.